Hi everybody. I'm Fang, and I'm an engineer with Arup's Toronto office. I work in the aviation team, and we are basically we're basically people that help plan airports around the world. And I think the important thing to note here is that aviation and transportation, there is that big overlap, but then aviation is not exactly like transportation, and we'll kind of touch up on that, but there are definitely transferable skills between transportation analysis and transportation engineering and aviation. And one thing that we like to emphasize in our group is that airports are basically now hubs into the region. So at any time you go to a different country, go to a major city, the first thing you see is the airport. It's the first impression you have of the place, and when you leave that place, the airport is usually the last place you see. So an airport is now basically a gateway to a new area, and the impression that the airport makes is very important for the city, the country, or the region, that area in general. So it is at this point it is there are a lot of focus on airport developments and how they treat passengers and how the passenger experience is. And when we're talking about airports, there are basically four main categories of an airport, or four main subcomponents to an airport. The first one is aerodrome, and then there's airside, and there's terminal, and there's landside. So aerodrome is basically the entire region of space where aircraft are lining up to land, or the aircraft is taking off from the runway. So that's basically a lot of airspace and air travel coordination. So FAA and Transport Canada, they kind of handle a lot of the planning of the aerodrome, and they make sure that no buildings are going into that space, and they make sure that that area is free of other traffic and free of drones and anything that could kind of impact aviation operation. And then the next one is airside, is basically comprised of the runways, the taxiways, the aprons, and basically everything that the aircraft kind of touches upon. And then the terminal is where the passengers get to interact with the aircraft. So boarding, deboarding. If it's an international airport, there's immigration, and then there's all that security checkpoint, check-in, and baggage reclaim. And then on the flip side of that, there's the land side, which is the curbside parking garages and how people get to the airport. So what our group does is we focus a lot on the terminal, and we touch up a little bit on the air side. And to give you a bit more background about the group in Toronto, and basically Arup in general, Arup is an international firm. We have pretty much offices in pretty much every major city in the world. The headquarters is in London, but we're right now, I think we're 16,000 employees around the world, and again, on the map, you can see all the offices. And within airport, the aviation team is a specialized team that does planning and engineering for airports. And there are three major hubs. One of them is in Toronto, and then we have two others in London and Hong Kong, and a few other satellite offices where there are about 2 or 3 employees that kind of specialize or have a bit of experience in airport planning. And on the grand scheme of things, the Toronto office is one of the biggest in terms of aviation expertise, and we are one of the basically hubs of excellence for aviation. And because of that, the Toronto office, the team that I'm here to represent, we have worked on some of the most prestigious airport projects in the world. And just in the last few years, we have touched upon airports in the Middle East, Asia, and many of the major airports in U.S. and Canada, including Pearson, Billy Bishop, and New York, JFK, the 3 airports in New York. West Coast, we have touched upon LA, San Francisco, Seattle, Portland, and the likes as well. And because of that, our group does have that, we have, with all of that exposure to the many airports in the world, we do have that repeated expertise on building simulation models and doing the analysis, so we can be efficient at that. And this really is kind of like a critical mass of employees that do this and make this snowballing effect for it to keep going. So what exactly is it that we do? You might be thinking. We basically analyze the different components of passenger processing facilities within a terminal building. So this ranges from check-in to departure security, inbound, outbound immigration, baggage reclaim, and so these are kind of the main things that we see as a traveler. We also look at aircraft gate allocation and airline assignment, and basically airline allocation strategies for an airport. And we do this with a few tools. We use Excel a lot, and we use other than that, we use industry-specific tools such as CAS or NAPA. So these are what we use to allocate aircraft to gates. And we use simulation tools, so discrete event simulation, to look at how the queues form and dissipate within an airport. So operation research is something that can kind of relate to that. And then we also look at pedestrian simulation, pedestrian microsimulation. So we use mass motion a lot. I think there's some exposure to this in this program to mass motion. I think Eric Miller's course has a little bit of that going on, and there's that great collaboration between UT and Arup on that front as well. And we can pretty much group all of our tasks into these 5 main categories. Again, it's aircraft gating, processor capacity, schedule analysis, passenger flow, and visualization. So all of these kind of make up the portfolio of the work that we do for clients, and we usually we can basically do these tasks at any point of a project. So when you think about an airport development project, either it's a greenfield airport, so a brand new terminal building, brand new airport, versus an airport expansion project, so Pearson is thinking about a new pier, or an airport's thinking about a new terminal, or extending one pier. Our work can come into any point of an airport's life cycle, and especially because if an airport is thinking about a new extension or a new pier, that means more passengers are going to go through the airport, and all of those passengers have to be processed by processor facilities. And if an airline is thinking about a different kind of operation at the airport, so if an airline wants to focus more on transfer passengers, then that also means a difference in demand on the processor facilities. And recently with COVID, there's all of that change in passenger patterns as well. So even as an airport is decreasing in traffic, or if they have to implement social distancing, it also means there's going to be a different capacity that the building can handle. So during that time, we have also worked with a lot of our airport clients to kind of determine their new capacity of the building, or if they need to revisit the flight schedules that they have agreed on with the airlines to see if passenger experience is still at an optimal level. So then, once we get into this, we kind of think about what the point of all this is. So what is passenger experience? It's basically circled around happiness. And then happiness is kind of a vague term, but our group has defined it as perception divided by expectation, or perception minus expectation, some kind of perception and expectation in a negative correlation. And at one point, a passenger might travel through an airport in Toronto, or then they go to a really old and busy airport, probably in the US. And then they can make that comparison between the Pearson experience and the experience at an older airport. And then they might go to a greenfield airport in the Middle East, or go to Asia, and then they can have those 3 dots. So then the passenger might think, oh, this airport's great, this airport sucks. Again, that's kind of a point to a passenger experience as well. The best experience anywhere can become the expected experience everywhere. So a passenger that could, quote unquote, be spoiled by a really nice experience can be really upset by something that they see anywhere else. To kind of combat that, there are kind of international standards for passenger experience, the level of service. I think some of you might be familiar with that when you look at roads performance if you have experience in pedestrian simulation, there's that too. But again, our work kind of is revolved around passenger satisfaction at airport journeys. And how do we achieve a good level of service? So we can influence terminal infrastructure, and we can work with the airport, we can work with the airlines, and we can kind of inform them that to make things work, you need to have this many security lanes, this many check-in desks, and then we can have some influence on how they can staff these positions. But then when it comes to the other two pillars that make up the level of service or the airport experience, which are government policies and regulations, and then passenger behavior, we really don't have much of an influence to that. Government regulations could be new policies at airline security or airport security, or inbound and outbound immigration policies. So very few times we do work with a client that can have that kind of influence, and this is more like in the Middle East, where I think one of the projects was on inbound immigration at one of the airports there. So then our project manager was speaking with the client and said that, okay, if you keep up with this kind of inbound immigration procedures, you're gonna have this much queue. And then the sheikh over there just said, okay, we're gonna make it better. We're gonna have upgraded immigration experience, so we're gonna get rid of that queue. So that's one of the better scenarios where our client does have that kind of influence. But in most cases in North America, we kind of don't have that, and that is a limitation that we have to be cognizant of when we do the work in aviation. So getting into a bit more nitty-gritty on what we do, our work really has many sub-modules of expertise or of processes that we do. Whenever we get a project, we basically have to speak to the client and have that good level of communication to set up the simulation parameters. We have to determine what the demand is at that airport, and then we can think about allocating that flex schedule or that schedule onto the terminal building in terms of where the aircraft is gated. And without that information, we can get on to the next step, which is to look at the passenger demand through the building with our discrete event simulation models to kind of either determine the queuing that would happen at the numerous passenger processing facilities, or we can determine what provision we must have at those facilities to achieve a good level of service. So in terms of wait time and queue sizes, or resulting queue sizes. Then we can kind of extract more information from our discrete event model, and we put that into mass motion, and we can have a nice visualization tool to kind of show the passenger queues, and that also helps us model the passenger behavior in a geometric sense, where we look at the geometry of the building, we look at bottlenecks within the terminal, we look at places where passengers have to make a U-turn, so we can kind of comment on good passenger flow in that building, and we can look at cross flows as well. And at this point, we can start getting to the interface to any kind of ground transportation centers. So, for example, some of the new builds in Asia, they've also considered a very substantial rail connection to the airport as well. So I think Pearson also has some of that, where there's that big consideration in front of Terminal 1 where they're thinking about putting in a regional rail line. I think some of you might have worked on that one too. So at the end, we have our outputs. We have terminal facility requirements. We have facility level of service. We have a nice visualization for passenger congestion. We can kind of comment on the level of service for passengers as they go through the building. And then we can also look at vertical and horizontal circulation, so the elevator, escalators, and kind of staircases as well. So again, there are two types of simulation that we use in the group. One is the discrete event simulation, which again comes to operation research. So we look at passenger processing, queuing, and waiting, the level of service in terms of wait times, and then we look at, and then this is what we call numerical results, because the results show up in tables, and we present to the client, these are your wait times. And then the other one is the passenger flow simulation, which is done in mass motion. So this is like corridor space programming, geometric analysis, and anything to do with that. And that is a graphical results, and so that shows up in videos, and we show heat maps to the client, and we kind of take them through what these design decisions might mean for passenger flows at the airport. And just like every kind of modeling that's done, we do need to look at the demand input, then we look at the processor facility, and at the output side is the level of service. So the demand is really where things get a little bit different from the general transportation modeling side. So because with traffic simulation, we have our favorite 4-step model, which starts with trip generation, trip distribution, mode split, and traffic assignment. And in the world of traffic simulation or traffic analysis, the demand is really nebulous. We think people want to go from one part of the city to another. We have some survey data from Transportation Tomorrow or any kind of data sources, but we're not really sure. We don't know. But in airport and aviation, this is more concrete in a sense that airlines and airports have agreed on a flight schedule. Tickets are sold many months in advance, so we know what's going to happen at the airport in terms of demand to some extent. For example, Pearson has daily flight schedule kind of already figured out what flight is coming, what flight might be delayed, what flight is a little early. And after that, we also have good understanding of what a passenger does in a building. So we know certain percentages of passengers wants to do check-in at a desk. Certain passengers are happy going to check in at a kiosk. Certain passengers can check in online. So all of that information is available to airlines. And if our client is an airline, they will have that information in very disaggregate or aggregate data that we can rely on. So all of this is, in terms of demand, we have a good concrete source of data for that. And with that as well, we have a good processing flow or a good flow through the building as well. So we know what the splits are, what type of passengers can go through fast track security, what types of passport they're using, so they can go to different immigration lanes. And that's again, in aviation, it is very fortunate that we do get to work with this kind of data, and this makes our model a bit more robust, and we can kind of rely on the results a bit better. So other than passengers, we have bags and aircraft demand. Again, the similar idea comes in that sense. So we kind of know how many bags each passenger is checking, where the bag needs to go, and as well, same thing for aircraft. Barring any major delays due to weather patterns or anything major like that, we kind of have a good idea of when the aircraft is coming. So we can put these aircraft on the gates to kind of process them. So one very standard way for us to kind of represent demand at an airport is with an hourly throughput or with an hourly demand graph. So this one is kind of a typical airport with lots of origin-destination passengers, and origin-destination passengers, we shorten this to OD, so it's like an OD matrix, but it's not really an OD matrix. An origin-destination passenger is basically someone that enters the city or leaves from the city, and this is as opposed to a transfer passenger where you connect from one flight and you depart from another flight. So airports that want to cater to either OD, predominantly OD demand versus transfer demand have to be designed a little bit differently. So this one you can tell it's OD, not because most of the lines there show OD, so the blue line is very high, so you know there's a lot of OD. But you can also see from the pattern at this airport that this is an OD airport. And one of the things that kind of gives that away is that there's a major departure peak in the morning. And there's basically no departures in the late night time because there are curfews that have to be followed for airport in most cities. When an aircraft takes off, it's really loud for the neighborhood. So if you live in Mississauga, you probably experience that. So that major peak in the morning it represents that morning rush to kind of get out of the city. So these flights are most likely short-haul flights, or a good chunk of these flights are short-haul flights to neighboring cities. So if it's in the U.S., it's probably a flight from New York to Boston, New York to Washington. So then, business people go have their meetings later in the day. They fly out in the morning. They do that. And the other thing is, this is when pilots wake up and they can start working. So a lot of airlines want their pilots and want their planes off the ground as soon as possible. So a plane that's flying makes the money. A plane that's sitting kind of costs them money, and it doesn't do anything. So that's one thing where you can kind of see that this is a major OD hub, or this is some kind of an origin destination airport. On the other hand, we have transfer hub airports. So here you can kind of already see the major difference there. And this is an airport in the Middle East, and we can also kind of get a bit of hint to that as to why this is the way it is. So at a transfer hub, traffic is usually done in banks. So major banks here, where we have arrivals. So all the aircraft are coming in, they're landing. They take passengers in from all parts of the world. And then passengers kind of get off the aircraft, go through transfer security, do all that fun stuff, and then they immediately get on the departure bank, so they leave right after. So if you buy a ticket from an airline that does a lot of transferring, for example, Emirates or Qatar or Etihad, they operate huge transfer hubs in the Middle East. You'll probably have a transfer time that's just a couple of hours. So they really want you to get into the airport, do some shopping, and then get back out. So they got three of these hubs, three of these major banks going on, and that's a dead giveaway that this is an airport that focuses on transfer passengers. And the other interesting thing about this one is that you can kind of notice that there's barely any departures starting mid-morning. So in the Middle East, it's really hot, and those airlines they operate very large planes to feed that transfer hub, and that really, the reason for that is, as a transfer hub, you can take demand from your feeder cities, and they don't have to be major cities anymore because everybody's coming in here to your transfer hub and then they're going back out again. So let's say you have two smaller cities that's in Europe and Asia, there's not enough demand for a direct flight going between them, but there is enough demand from this small city to your hub, and then the people want to go to any other part in Europe or Africa, then they can go through the Middle East as a transfer hub. And since that's the case, you can fly pretty heavy planes with fully loaded passengers. You can have lots of demand there. And these big planes, they take a lot of runway to take off. And as it gets hotter, the air gets less dense. And when the air is less dense, it creates less lift. So for that reason, we don't really have a lot of departures where it's hot, or when it's hot. So they have this really big midnight peak. And that's one of the things where, in that parts of the world, you can kind of bypass curfew laws, where we can be loud at midnight, because otherwise we're not doing any business. So that's an interesting part of aviation that we learned, I learned after a couple of years. And so with all these demand and the show up, or with all this kind of demand patterns at an airport, the passengers have this thing called show up profiles. So again, a lot of airlines have that data as to when their passengers show up to the airport for a flight. So if I have a flight at 10 a.m., I can choose, I have a choice. Do I want to go at 7 a.m. or 8 a.m.? So that's like a 2 to 3 hour show up profile. But if I have a flight at 9 a.m., I technically have a choice. Do I want to go to the airport at 5 a.m. or 6 a.m.? But I really don't have a choice. I don't want to go to the airport at 5 a.m. So for that same reason, if your flight departs early in the day, your show-up profile is more compressed. So if your flight is really early, you're just going to put up with the fact that I'm going to be a bit rushed at the airport. I'm just going to get some sleep and then get on with my day. But if my flight is like 2 or 3 p.m. or if my flight's at 6 p.m. and my hotel kicks me out at noon, then I'm going to have a 5-hour show-up profile at the airport, unless if I find something else to do in the city. And because of that as well, if we apply the show-up profile to the various passengers, especially during the morning peak here, the passengers at between 6 to 7, they're going to show up at around 5-ish. The passengers at 8 to 9, they also might show up at 5. And the passengers at 9 to 10, they're probably going to show up 6, 7. So we have that compression of demand of passengers relative to the flights in the mornings. And that really makes the morning peak even worse. Worse than what this graph shows. And again, if we're using classical ways to do airport analysis and to do facility planning, we won't see that. We won't get that. But once we get into simulation and we really apply a show-up profile to different kinds of passengers in the morning at different time frames, then that can really get you that behavior, and then you can kind of plan your building accordingly. So again, a lot of our clients, they would have been tripped up by this fact. They would do their back-of-hand calculation to see, oh, this doesn't work, this doesn't make sense. And then we had to show them, well, this is because you have different show-up profiles in the morning. And that's something that really drives home the point to a lot of clients. So after our passengers show up at the airport, they go through all kinds of processes. Some of them, again, check in differently. Someone that's really savvy with the fly, they'll do mobile, and then once they do their mobile check-in, they got their checking passes on their phones, and then they go drop their bags. Some people might go to a kiosk. The kiosk might say, okay, excellent, here's your boarding card, or the kiosk might say, I don't know who you are, you need to talk to a person. So we have all kinds of data on what kind of passengers, what kind of experience a passenger might have, broken down into percentages. And then we apply that to the passenger, and then we kind of put them through the building. And this is where our numerical simulation or our discrete event simulation comes in. So this is a tool called Simio that we use. I think the industrial engineering program might have a bit of touch up on that tool. It's basically everything here is a black box. So everything that the operation research prop tells you is we kind of put it in here. And we can say this process has 20 servers and they follow some kind of distribution in terms of processing rates, and then the Simio will end up spitting out what queues we're getting and how many passengers we get in that queue. And this is kind of an example of what this is an example of what a Simio model might look like. This is Montreal. I think I can say that. That's not confidential. We have Canadian Airlines, other domestic airlines, and then these are international airlines that kind of go around. In Simio, everybody's walking on the line, so they don't know that they're bumping into their friends or their enemies. They don't know that they're bumping into walls either. So here, what we really do is we have passengers show up at the curb, and there's some kind of semblance on how long it takes for them to walk somewhere. But in most cases, it's fairly it's a pretty big approximation on the walking times, and then the passengers get to a server, we say. So these things are servers, and then they do their operations to go through check-in and security. And after that, we kind of take our output from Simio. So Simio will tell us your wait time is this much at these processors, your queues are this much. We compare it against the international standard. So this is the Airport Development Reference Manual. That kind of everybody in the world is using to plan their airports. I think those of you that are taking the airport planning and engineering course might see some of this. So at different parts of the airport, you have different standards for passengers. So if you're checking in, you want to have some kind of a wait time target. If you're full service, you kind of slightly problematic. You have to talk to an agent. So we kind of allow you to wait up to 15 minutes before you see an agent. If you want to go through a kiosk, then you kind of want to cater to that, and we want to make it a bit faster experience. So we're designing check-in lobbies to kind of have shorter wait times for that kind of passenger. And then, depending on which part of the airport you're in, you may or may not have your checked luggage. So if you have your checked luggage, you occupy a bigger space, and then once you've dropped your luggage, you can kind of, you're a little bit more mobile. So all of that is kind of here, and we take our outputs from our numerical simulation software, and we compare it against these standards to see how the building is doing. So then we kind of determine the positions required, the queue spaces required, and then we take all that information and we give it to the architects. So at this point, the architects are really planners for the building, and that's another distinction between the group that I represent and I would call them the architects. So we do all the mathematics behind it. So we run all the simulations, we prepare the reports, and then we give that requirement to the planners, and they would be the ones that will figure out, I have 20 lanes, I need 20 lanes, I need to put them in the building somewhere. So they'll do that, and it's a different set of skills to do that as well. But there is a different group that does that. And one of the examples that I can talk about is the Taiwan airport. So it's Taoyuan Airport Terminal 3. It's a 500,000 square meters building. This development is the one that this project is looking at, and this building is going to handle 45 million passengers per year by the time it's complete. So as a comparison, Pearson itself, the two terminals at Pearson, they combine 50 million passengers per year. So this building is 90% of Pearson, and then the other two out here they're going to do another 40 million passengers. So when this thing is all said and done, there's going to be 80 something passengers going through that. 80 something million passengers going through that per year. And so for that project, we did the numerical simulation. We figured out what they needed, and we fed that information back to the planners, and the planners and the architects worked together, and they updated the building footprint, and they updated different parts of the building to kind of accommodate the requirements. And what happens after that is that they would feed back a new design or a new set of floor plans to us, and we take those plans and we put together the passenger flow simulation or the mass motion model. So I think this is this place. So this is the building. It's not blank. One second. Technology. Okay, it's pretending. Yeah, so this is our mass motion model, and this is the check-in hall for that airport. And we're simulating passengers, and now they're aware that there are other passengers around them, just like what the prof probably told you about mass motion. And they're going through all of our processes, going through queues. So all of these, they are calibrated to certain passenger behavior, certain passenger mobility status, like walking speed and preferred space around the passenger. And we have passengers kind of dwell on the air side to kind of represent some kind of shopping experience. And then this is kind of the arrival profile or the arrival passengers. They're coming in, they're getting into these gates, they're coming off of the automated people mover, the trains. And here's another view where passengers are coming in on the sterile corridor, and they're entering, doing immigration here, or they're doing transfer security here. And here we can see two different types of immigration. And at the end, arrival passengers, they're claiming their bags at bag reclaim belts. We kind of have simulation on how long a passenger needs to wait for their bags. And here's where we kind of visualize that, and we show what each area of the airport might look like and how crowded it gets. So here is kind of the land side where they meet their families and friends. So these are greeters. And through all of that, we kind of compile these videos and we show the client how their airport is doing, and also along with the report, level of service, heat maps, in various parts of the airport, and we kind of identify any points where the level of service gets a little too low. So in airports, we kind of go for level service C, or sometimes we accept level service D, and we know level service A and B is really like above and beyond. Only a few airports in the world kind of claims to strive for A and B, and then all airports are kind of going for at least C. So with all of these information, we can also inform other design decisions in the airport. So one of them is hold room occupancy, how big we need to build the hold rooms, how many chairs we need to put in there. And with any kind of occupancy or any kind of accumulation information, we can also inform the heating and cooling department. So the mechanical engineers sizing air AC or sizing HVAC. So ventilation and air circulation. We can also inform decisions on fire escape. What we can kind of anticipate as total or maximum accumulation throughout the day. So then they can size the egress staircases to allow all passengers and all passenger and staff to leave within a minute in case there's an emergency. We also touch up a little bit on the curbside. So there's a very good collaboration between our team and the transportation team in other offices and within our own office to come up with demand for the curbside and what kinds of traffic we can expect to see there. And another one is where we can dive down quite deep into a result interpretation. For example, these are immigration kiosks at an airport in Europe, and the initial plan was to have just this many kiosks, and then we kind of went over with the client. We agreed on all the parameters. We got all the data we needed, and we put together the model. And we found out that this is nowhere near enough. We need to put more here, and then queuing becomes a problem. So then we needed to have relief queues here. And a little bit, and then the client said, okay, what if we put queuing up there? So then the problem with that is you also have a big flow of passengers coming in here. So if your peak is happening from this flow, they're not going to be able to see that queue. So to do that, you're going to have to direct them upstairs to go to that queue, which is a terrible experience. And we told them that this is a terrible experience, and they said, okay, fine, we'll just add on even more. And then I think at that point is where they put in this queue here. So this is one example where we're really going down deep to kind of show the client or show the geometry what some of the challenges are. And again, this is another challenge of running old airports, because these airports were built before all these policies were in place, and these airports were built before the passenger count got to this level. So a lot of times when we work with these older facilities is to put the new demand in there and make things work. And again, this is also hats off to all the planners. Question?
What's the difference between the blue and the gray people here? Like when this simulation started up, I saw a bunch of gray people.
Yeah.
And they were like going straight through, and then the blue people were waiting. Is it like passport differences or something?
That's exactly it. Yeah. So here is when the gray people were people with EU passports. The blue people are other people.
Okay, so they're like, oh, welcome home. It's like a Canadian going into Pearson versus
that's right.
Someone else.
Yeah, that's exactly it. So in all of our modeling, we have to differentiate what kind of passengers these are. So what passport types, and they're eligible for one thing versus another. So you have to kind of have that distinction. And in the previous video too, so departure passengers, you can have different types of check-in and security, and arrival passengers. If you're transferring or if you have a Taiwan passport or anything else like that. So being cognizant of time, I'm going to go through this really quickly. Heat map. So this is a rail station in front of an airport, and we got 4 different lines out here, and our client really wanted to see an overall heat map of the area, and then they saw all these reds. They're like, oh my god, my station is terrible. So we have to also kind of be a bit reassuring at points. So we have to tell them what's happening here. What's happening here is, as the train door opens and you have a full train, everybody's coming out, and then at the same time you have people on the platform. So at that time, your demand on the platform is really, really high, and that's kind of shown here by all these spikes every time a train door opens. So your density goes really, really up to LOSF. So we have to tell the client that, look, this is okay. It'll pass. Only happens for 20 minutes during the peak hour. And then we show, like, what happens during the day is most of your passengers are in the blue to green, which represents level service C, and very, very few people would get into D, E, and F, but then your peak hours are the ones where you have a bit of challenge. And if you design to the peak hour, to get to C for the peak hour, you're really oversizing the facility. You gotta double your budgets for that. So then they have to make that decision whether or not they want to do that. And then lastly, this is kind of a bit of an overview on some of the projects we've worked on. I can't say what they are because they're confidential. And then we did some work for social distancing. So as we go through so I'm gonna skip that last one. As we're doing security, so we normally you can kind of allow 5 people to kind of open their bags and divest their things, to go on the X-ray, and then here you can kind of allow 2 or 3 people to accumulate here before they go through the metal detector. And then here there's some certain percentage of chance that you'll set off the metal detector and someone's going to have to scan you, make sure you're okay. So there's all kinds of accumulation that you can allow here, and also accumulation that you can allow here as they're repacking their bags. So this is under normal circumstance, and within that numerical model, so Simio, we can kind of tell that this throughput will get you 180 passengers per lane per hour. But as you have to do social distancing, so all of a sudden your 5 positions become 3, and your 2 positions become 1, and then you have to space people apart, then your throughput also drops. So all of a sudden fewer people can divest at the same time. So we can kind of see a 40 to 50% throughput is reduction. And a lot of our clients, they really want to see why that is, and they can see that as well. And then lastly, we have limitations to everything. All models are wrong, some are useful. So if we have garbage information in, it's going to be garbage information out. And a lot of this is data intensive. Anybody who's worked on mass motion here probably knows that when you run a mass motion model, you generate a huge database. And then you have to kind of store that database somewhere and read it. So that with mass motion, same thing with our Simio or the numerical model. And then you have to interpret it to the client. If it's just red and you say nothing, you're going to freak them out. So you have to tell them a little bit about why this is not a problem. And that's really why, as engineers, you get paid the big money, or big-ish. You get paid to interpret the data, because otherwise we're going to all be replaced by AI, and that's really kind of my closing point at this point. So again, thanks everybody for your time today, and I'm open for questions.